So let's dig into simple regression in SPSS. All right, so the assignment you'll see from Canvas was to write up a response to the question using simple linear regression. What influence, if any, does socioeconomic status have on students' mathematics achievement? And first, of course, we need to go through the assumptions there. And sorry for the flickering. Apparently, there's an issue with the newer update of my operating system. So assumptions for regression, we need to check if things are normally distributed, including residuals. And we need to examine relationship between residuals and the predicted variable. Then we can look at the results of that. And the first three questions of the assumptions there about whether data were randomly collected, whether individuals are independent, whether things are continuous variables, those are all answerable without statistical examinations of any kind. We can look at the data and see that the data are in fact continuous. If we're looking at PV1 math and SCS, they are definitely continuous variables. Individuals being independent of one another is potentially an issue because students can be nested within schools. So that could be problematic. And data were randomly collected. It is a random selection, although it is highly complex. It is not a simple random selection, random sample. But nonetheless, there is randomization involved in this data collection. And now let's examine whether or not the data are normally distributed. So let's go to Explore. We can put both PV1 Math and SCS in the dependent list. Let's go ahead and grab histogram, normality plots. And that looks okay. All right, let's see what we get. It's taking a very long time to run this. Okay. So 64,625 people in both PV1 Math and SCS. And we're looking for normality here. So skewness and kurtosis values well within the plus or minus 2 range. Of course, the KS test spits out these statistically significant results, implying that there is non-normality, but remember that we're dealing with a very large sample size, and these normality tests are highly sensitive to large sample sizes. So we're not going to put too much stock in that. Let's see what other evidence we have of normality. If we look just visually, PV1 Math looks great. The QQ plot of PV1 Math looks great. If we scroll down to SCS, SCS does look skewed left. And the QQ plot, we see some trending away here in the top right. And you see from the box plot that there are some outliers on the left side, on the lower end of the scale, which are going to be these down here. That's potentially an issue. And if we scroll back up, let's just check that again. The skewness and kurtosis values look well within range. So there's a potentially problematic, it's potentially a problem that SES is a little skewed to the left. All right. So if we're thinking about those first items there, dependent variable and dependent variable are not both normally distributed. The independent variable may be slightly skewed left. It may have some skewness problems, which may make our results a little inaccurate. And let's look at the rest of this now. Okay. So if we go to regression, linear, and put PV1 math as the dependent variable, because we're assuming SES is influencing PV1 math, meaning that PV1 math is dependent on socioeconomic status, which would mean that SES is not dependent on anything in this model. Let's go ahead and grab the confidence interval. Under plots, we want to examine the residuals against the predicted value or the dependent variable. So we're going to put the z-score of the residuals as x, the z of the predicted value, the z-score of the dependent variable, in this case PV1 math, as the y-axis. We also, in this box here, want to see the histogram and the normal probability plot for the standardized residuals so that we can tell if the residuals are normally distributed. So this is to check if there's normal distribution of the residuals. This is to examine the relationship between the residuals and the outcome measure. If we see a pattern to this, it would imply that, for instance, higher math scores result in data points that are farther away from the regression line. If there was a positive relationship, that's what it would mean. But we don't want to see that. That would mean that it's not linear anymore because the points are trailing away from the regression line in a specific pattern. All right. Click OK. It's still running the regression. You can't see it in the screen. It's off the screen, but there's a little thing in the bottom right that will tell you if it's still running, so you know if it's doing something. All right, the model summary tells us that R is 0.471. Since SES is the only thing in the model, this value is the correlation between SES and math scores. This is a moderate value. R squared tells us what the accuracy of this model is. It tells us the proportion of variance in math scores that is being explained by the model. In this case, the model is only SES. So this means that 22% of the variability we see in math scores can be explained by SES. That's not a huge number, but it's adequate. It's not great. The ANOVA table tells us that this model, the overall model, is statistically significant. The F-score is ginormous, 18,456, which means that this p-value is going to be extremely small. The problem with this is that this could be influenced by the really high sample size. So we have to be careful and withhold some judgment here, but the overall model is statistically significant. Here's the coefficients table. You see SCS, or pieces measure of SES, ESCS, with a coefficient of 35.59, meaning that for every increase of 1 in SES, which this is standardized, so we can be more specific, every increase of 1 standard deviation in socioeconomic status results in an increase of 35.59 points in students' math score. The t-score is 135. That is extremely large, which means this p-value is going to be extremely small. So this SES variable is statistically significant, and the confidence interval is very tight. In the population, we would expect the true effect of SES on PV1 math to be about between 35 and 36 points for every increase of 1 standard deviation in SES. If we scroll down, we have not yet checked all of our assumptions, so we can check the rest here. This looks normally distributed, and the probability plot confirms that. The points lie very close to what would be expected, which is this black line in the middle, and there's some gray shading behind it, which is where the points are. Remember, there's over 65,000 points, so you can't see them individually. And then here is the plot of the standardized residuals against the standardized predicted value. So the z-scores of the residuals versus the z-scores of PV1 math. It doesn't look like there's any inherent relationship. And so we would claim that there appears a linear model appears to have been appropriate. And that is the last assumption that we needed to check. And that is essentially how you would interpret the results here of this simple linear regression model. So if we were going to type up the results, we would start by making sure that we explained which assumptions are met, which are being violated, along with evidence of why we make that claim. Then you would state that the overall model appears statistically significant. F with degrees of freedom 1, 64,623 equals 18,456.323 with a p-value less than 0.001. The correlation of 0.471 and an R-square value of 0.222, indicating that about 22% of the variance of the variability in math scores can be explained by the model, and a moderate correlation, and interpret SES and report the t-score, p-value, and confidence interval along with it. And we will add to this next week some other things to be thinking about. We have not talked about effect size or anything like that, so we will be talking about that, as well as what happens when we add more variables to this list. All right, and I will see you next week.